Hello everyone, and welcome to the fifth and last video of this series. Today we will finish our short journey in the world of semiconductors by applying what we have learned during this chapter to understand one of the most important building blocks in modern technology, a p-n junction. So let's first give an intuitive idea of what this video is about. A p-n junction is just the boundary between two types of semiconductors, a p-type semiconductor and an n-type semiconductor. We learned that impurities add two types of charges, mobile charges and fixed charges. Now, in a p-n junction, things are quite interesting because both positive and negative mobile charges can diffuse to the other side. These generate a charge distribution across the junction such that, in this example, negative charges are going to accumulate on the left-hand side and positive charges are going to accumulate on the right-hand side of the junction. And diffusion typically extends about 1 micron. Now, this is very interesting because this charge profile generates a potential barrier, also known as contact potential, that for electrons that want to cross from the right to the left goes like this. And the same goes for holes. There is a barrier that we need to overcome to cross from the left to the right. And by the way, notice that I have drawn the potential profile the other way around for holes, and I still call it barriers. In a moment, we will see why. But first, let's go to momentum space. When we have a p-type semiconductor next to an n-type semiconductor, the dispersion on each side of the junction with the respective impurity levels looks like this. To generalize this discussion, let's replace this more or less complicated band structure by these blocks. As you know from statistical mechanics, one requirement for the thermal equilibrium is that the Fermi level must be constant across the material. Now let's focus on the bottom edge of the conduction band and the top edge of the valence band, simply because both types of carriers are going to accumulate here. To have the Fermi level that is constant across the sample, there must be a region, also known as the depletion region, where the edges of both bands shift linearly their energy positions from one side to the other. Let's take a closer look. We know that on the side of the n-type semiconductor, we have electrons in the conduction band and no holes, and in the valence band. On the side of the p-type semiconductors, we have a lot of holes in the valence bands and nearly no electrons in the conduction band. Now, pay attention to this small diversion. When we apply an electric field, electrons behave like balls in an inclined plane. They just will fall down from the anode to the cathode. Electrons, however, are a little bit different. They behave more like bubbles, because in essence, they represent the emptiness in a sea of electrons, just like bubbles represent the emptiness in water. For this reason, they will float from the cathode to the anode, and potential barriers are reversed for them. This interpretation seems quite intuitive, and is actually physically sound. Now, let's go back to the p-n junction. As we saw earlier, there is a preferent direction for the current. This is the forward direction for the current, which will be present when we apply a voltage that is greater on the left than on the right. As a result, electrons are going to flow from the right to the left, and holes are going to float from the left to the right. If the voltage fall is high enough, an electron and a hole will recombine in the junction, liberating heat in the process, and effectively generating a current in both sides of the junctions that goes from left to right. Now, what would have happened if we reverse the current? Well, the answer is pretty simple. Nothing, because there aren't electrons in a p-type semiconductors and there aren't holes in an n-type semiconductors. In other words, a p-n junction works like a valve of charge, controlling the flow of current. This invention was discovered in the Bell laboratories in 1939 and has become an essential part in electronics nowadays, where it is usually represented by this symbol. Speaking of electronics, This would be the intensity, the voltage intensity profile that you could obtain if you connect the diode to an adjustable direct current. In the forward direction, as soon as you pass a certain barrier voltage, you get an ohmic response, which is linear. In the reverse bias, you actually have to apply a voltage that is about 10 times greater to have a current, and it comes with a huge increase in resistivity. So this is a PN junction. But what about applications? What can we do with a diode? Well, we can, for example, design a rectifier, a device that converts alternate current into direct current, because every time the voltage is in reverse bias, the current is blocked. This is the so-called Zener diode, and it produces a voltage profile like this. There are ways to make it more stable using a rectifying bridge, for example, with a capacitance, but this goes beyond the scope of this video. We can also use the diode to generate light by engineering a PN junction and carefully selecting the components. You can, in principle, generate light out of every combination instead of heat. And the opposite process is also possible. Light could, in principle, create an electron-hole pair, which in turn could generate a current. And this could, in principle, be converted into a voltage difference for later use. This is the essence of solar cells. The range of technological applications for a PN junction is immense, and we could be talking about this for hours. However, it's time for me to end this series of videos. It's time for me to say that I hope you learned something out of this and wish you all the best for your future exams. It's time for me to say thanks for your attention and goodbye.